Hello, my children. So, we are starting on our video, and Brooke is laughing, and Emma is laughing, and we're all laughing at me because I'm calling you my children. But you are my children, so we're going to continue, children. We are starting on slide number 30. I want to talk about the 4 quantum numbers when, even though your PowerPoint and the book says there are 3, we know that there are technically 4. So principal quantum number, we will designate with the symbol N. And principal quantum number N, we know describes the energy level for that electron. So wherever that electron is residing, or that electron cloud. Energy level, we can find that super easy by just the row of the periodic table. So if we had our periodic table out and I asked you, what energy level is beryllium in? You would say the second energy level because beryllium is in the second row of the periodic table. If I asked you what energy level aluminum is in, you would say 3. Why? Because aluminum's on the 3rd row of the periodic table. So whatever row we're on, we know that's our energy level. And of course we have a couple exceptions for that. Remember that when we are in the d orbital, that goes down by 1. When we're in the f orbital, it goes down by 2. So think back to electron configurations, which we'll get to in a few slides. Actually, like several slides, really not a few. If we think about electron configuration, and let's say, for example, I want to do scandium. I would say 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. So remember that the d orbital goes down by 1 if we're thinking about energy level. F orbital will go down by 2 if we're thinking about energy level. Okay, second quantum number is the angular momentum quantum number. We symbolize that with the it's a cursive L, actually. So this quantum number defines the shape of the orbital. We have 4 particular orbitals that we are interested in. Those orbitals are S, P, D, and F. In terms of their shapes, because remember, this is what designates the shape. S is spherical in shape. P is a dumbbell in shape. D would be cloverleaf for the most part, except there's one that kind of looks like 2 pacifiers that are linked together by a ring. I don't really know. So there's one that's kind of wishy-washy, but in general sense, it's cloverleaf. And F is undefined because some of them we just don't really know, and we think that they may be different than what we previously thought. Okay, so principal quantum number, that's N, that's energy level. Angular momentum, we're symbolizing that L, and that means shape of that electron cloud. And we know there's 4 orbitals, so 4 shapes, which are S, P, D, and F. Spherical, dumbbell, cloverleaf, and then just undefined. Now, in the past, Schrodinger has come up with these symbols like L, or we've come up with N to be energy level, and we have specific values that we've given to these shapes. So quantum numbers, we can actually give like a number for these designations of energy level and angular momentum. So it says if we have an s orbital, the L is equal to 0. If we have a p orbital, we say L is equal to 1. If we have a d orbital, L is equal to 2. F orbital, L is equal to 3. The new AP Chemistry curriculum now states that we do not have to do anything with these quantum values, with the 0, or that the angular momentum, or L, would be 1 if it was a p orbital. So in terms of the orbital, or the quantum numbers, with like the value of L, the value of N, the value of M sub L, which we'll get to on the next slide, you will not have to write any of those out. I just want you, though, to be familiar with it if you see it, because you're of course probably, when you take like your 2nd semester chemistry class in college, you may have an older dude who is in love with quantum numbers. So allowed values of L are integers ranging from 0 to n minus 1, so energy level minus 1. So we could have 0, 1, 2, or 3 for values of L. And our 3rd quantum number is the magnetic quantum number. We're going to symbolize that as M sub L. M sub L. Magnetic quantum number just tells me how many orientations of each shape are there. And I want to think then, like, how many shapes can I have for each orbital? So S, we said, was spherical. If we're thinking about this in like 3 dimensions, and I have S or a sphere, it doesn't matter how I orient that sphere, it's going to look the same regardless. So S only has one shape. That's why we can get one S orbital. For the P orbital, that's dumbbell in shape, we can orient that along the x-axis, the y-axis, or the z-axis. So because of that, we actually have 3 p orbitals. If we go along with that and think about orientations for d orbitals, there are 5, and then the f orbitals, there would be 7. So 1 shape for the s orbital, 3 shapes for the p orbital, 5 orientations for d, and 7 orientations for f. And in terms of like quantum numbers, if we're using the L's and the ML's, those values, it says that allowed values of ML are integers ranging from a negative L to a positive L. So let's say, for example, we were in the p orbital, and I know that p is equal to L that's 1, right? Because on the last slide it says that if we're in the p orbital, then L equals, if we're in the p orbital, L equals 1. So then that means that ML can range from a negative L to a positive L. So it could be a negative 1, 0, or a positive 1. And really that doesn't mean a whole lot to us right now, and it probably won't mean a whole lot to us because we don't have to be tested on this on our AP test. Okay. So S orbital 1 orientation, P orbital 3 orientations, D is 5, F is 7. Let's keep going. In terms of our magnetic quantum number, they have a relationship within energy level, angular momentum, and magnetic quantum number. They have this table in your book, and then all of the possible values for quantum numbers that we could get here. So all of this, though, really, on your AP curriculum, we will not be tested on this. They just want us to be able to say that we know there are 4 orbitals. Those orbitals are S, P, D, and F. We know that S can have 1 orientation. We know that P can have 3 orientations, and it looks like a dumbbell. So they're going to ask you more, I think, conceptually, instead of having you do any of this. Okay. It says that orbitals with the same value of n, so if they're in the same energy, are going to form a shell. So we have that energy level. Different orbital types within a shell are called subshells. So I may have, if I think about my energy level, that's the shell. And then let's say that we're on the 2nd row of the periodic table. So I'm on the 2nd energy level. If I go across that 2nd row, I know I'm going to pass lithium, beryllium, and those are in the s orbital, and then I pass boron through neon, and those are in the p orbital. So I would say the s and the p, those different orbital types, those different electron cloud shapes, those are called subshells. Okay, so energy level can also be called a shell, and then the orbital types, s, p, d, and f, those can be called subshells. Okay, in terms of energies of orbitals, for a 1 electron hydrogen atom, orbitals on the same energy level have the same energy. Otherwise, we call another name for that, i.e., is that they are degenerate. So if I'm thinking of a 1 electron hydrogen atom, orbitals on the same energy level have that same energy. But as we increase the number of electrons, the repulsions between those electrons, if we're increasing the amount, we're going to have many, many, many more repulsions because we have that similar charge, so they're repelling one another. And because of that, we're going to get a difference in energy levels as we go across and down the periodic table. So we know we were going from our 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. So we're just moving across that periodic table. And the reason that stuff happens is because of the number of electrons are increasing. Because think about, as we're moving across and down the periodic table, the number of protons is increasing. So we're moving, as we're adding those protons, we're also adding those electrons if we're thinking about a neutral atom. So if all of these are just my neutral atoms, if I have that number of protons, I have that many number of electrons. So the more electrons, more repulsion. So because of that, the energy levels are not going to be equal to one another. So it says they are no longer degenerate. And we've seen this before as well, 1s, 2s, 2p, 3s, 3p. We did that with electron configurations, which we'll do here in just a second. S orbitals. We know that s orbitals are spherical in shape. So I can have 1s, we know there's 2s, 3s, so on and so forth. We said that this is called an electron density map. So that's just showing all of those blue little dots are representing where an electron is traveling, or the path of the electron. So I know that it's really concentrated here in the middle where the nucleus is located, because the electron wants to be around the nucleus based on Coulombic attraction. I see that as I get farther and farther away from the nucleus, though, that I'm not seeing as many blue dots around the outer edges of that electron cloud. And that looks more like spherical in shape, so we're just going to say s orbital is a sphere. So the radius of the sphere is increasing with the value of n. 2s is bigger than 1s, 3s is bigger than 2s, and that's because we can almost think about, I have 1s here. If I add another energy level, 1s is really like encompassed by 2s. And then if I think about 3s, I also have 2s and 1s kind of encompassed in that one as well. So as I add energy levels, we're increasing that amount of empty space for those electrons to move about. So radius of the sphere increases with energy level. Okay. In terms of s orbitals, we have a graph that we can use that's based on probabilities. These graphs are called radial distributions. So in terms of distance from the nucleus, and we're thinking about that just with radius. So the radius of our atom for distance from the nucleus and then it's going to be measured in angstroms. And again, we're calling this a radial distribution, and I think that may be on your next slide. Yeah, that's on your next slide too. So observing a graph of probabilities of finding an electron versus distance from the nucleus, we can see that we have these things called nodes. And a node on these radial distribution graphs is something that would represent that, or something that represents where we have zero probability of finding an electron. So if I'm thinking about on 1s, so I'm measuring the distribution of electrons around that, or in that 1s cloud, that 1s electron cloud shape. I see that my distance here is relatively small because that first sphere is very close to the nucleus. I have a very high probability of finding it close to the nucleus. Let's say that I want to think about, though, 1s and 2s. So let's say that now I'm at 2s. So now I have that first ring, and then I have that second ring. So I have some electrons that are around the nucleus in the 1s, and I have a lot of electrons that are around the nucleus in the 2s as well. But this node is where I would have a zero probability of finding an electron. So that means that those electrons that are there specifically for 2s are 2s's electrons. Those electrons that are there for 1s are going to stay in that 1s electron cloud. The electrons that are there, like I said again, for 2s are staying in that 2s electron cloud. So it's kind of like, let's go back and relate this to Bohr's model. Bohr's model, one of the things that he found that was right was that electrons have to have a certain amount of energy to jump between energy levels. And I'm never going to find an electron outside of one of those energy levels. And that's what this is showing. So the fact that we have a node here where I have an electron density here in the 2s and here in the 1s and nothing here, that's telling me that's the edge. There's the end of my electron cloud. I have a definite amount of energy then that an electron is going to need to gain to move from here to here. So that's another kind of, I think maybe help for us to know that Bohr was right in his case by saying that electrons can't be just somewhere in between our orbitals. So at least we got that from him. So again, just another radial, another radial distribution here. So this is 1s, 2s, 3s, and this is just, again, a radial distribution. I'm showing electron density and where I'd be most likely to find electrons based on distance from the nucleus. Okay, p orbitals we know are dumbbell in shape. There are 3 different shapes that we can take with a p orbital. One that's located along the x-axis, one on the y-axis, and one on the z-axis. So we know that 3 shapes for p. Remember, s has only 1 shape and it is spherical. D orbitals, there are 5 different orientations that it can make. So in the most part, we see these 4 look more like cloverleaf in shape, but then we have the crazy one that's like a pacifier on both sides, or like a, I don't really know, a dumbbell with a ring or tube or donut on it. I don't know. So there's only one that doesn't follow that trend, but as long as we know for the most part it resembles a cloverleaf will be good. And there are 5 shapes of those. In terms of, again, just another radial distribution. On this one we're seeing a distribution between 2p, 3d, and 3p. And for now, it may seem like I may be going over this one really fast, but we're going to do a couple worksheets with radial distributions either tomorrow or Thursday. I haven't decided yet. So we're going to do some more with this. So don't worry. We said before that there were 4 quantum numbers for our slides. Even though the slide said that there were 3, we really know that there are 4. So spin quantum number, which we'll just denote ms, spin quantum number is designating the spin of the electron, and specifically that's when we're thinking about it like in a magnetic field. So we know that the spin of the electron can have 2 different values. It could have a value of +1/2, or it could have a value of -1/2. Ultimately what happens, if we take a beam of atoms, we have that go through a slit, and then we apply some type of magnetic field to it, like we have a magnet here, we have seen that we get 2 different values, or the way that the electrons will move in their path because of this magnetic field is in 2 different ways. They could go in 2 different directions. It may, like we can see on the beam collector plate, it may veer right or it may veer left. So because of that, we know that an electron could have opposite spins. So it could be a +1/2 spin, or it could be a -1/2 spin. Typically, those that have unpaired electrons end up having a -1/2 spin. But we'll get more into that, I think, when we get into like chapters 8 and 9. So spin quantum number, electrons have spins associated with them, and their value would be +1/2 or -1/2, which we can see here. So our 4th quantum number, 2 values, +1/2, -1/2. So the way that they'll spin, either clockwise or counterclockwise. Okay, so now we're going to get into our electron configuration rules or principles. So we have Pauli exclusion principle, there's Hund's rule, and there's the Aufbau principle. So let's start with Pauli exclusion. The Pauli exclusion principle says that no 2 electrons in the same atom can have exactly the same energy. Therefore, no 2 electrons in the same atom can have an identical set of quantum numbers. So, since there are only 2 values that electrons can have, they could have a +1/2 spin, or they could have a -1/2 spin, each orbital could only hold maximum of 2 electrons with opposite spins, because that's the only way that electrons can act. They can have a +1/2 spin or a -1/2 spin. So because of that, I can only have 2 possible values in each orbital, and that is Pauli exclusion principle right here. An orbital can hold, because you tapping right here is going to make sure that you know that this is the Pauli exclusion principle, because you can't even see my hand. So an orbital can hold a maximum of 2 electrons. They must have opposite spins. That's my Pauli exclusion principle. In terms of electron configurations, we know that this shows how electrons are arranged in an atom. Whoa, totally didn't do that. Let's go back. Whoa.
You just hit previous.
Thanks.
You're welcome.
Okay, so electron configurations just means how the electrons are arranged in an atom. Or distribution, arrangement of atoms. We know it consists of 3 parts if we're writing an electron configuration. Energy level, orbital, so what shape that electron cloud has, and then how many electrons I have in those orbitals. So that 4 would represent I'm in the 4th energy level. That P would represent I'm in the p orbital, so I'd be in the p or dumbbell-shaped electron cloud. 5 would mean that I have 5 electrons that are in those orbitals.
Yeah,
Really?
this isn't good. Right click and hit next, I guess.
Okay, there we go. Remember when we did electron configurations, we also did orbital diagrams. So we said that each box when we did, oh yay! When we did orbital diagrams, each box represents an orbital. So remember that S only has one shape, so that's why it only has one box. If we were drawing something for P, how many boxes would we draw? 3, because there are 3 shapes. If we were drawing D, it would have how many boxes? 5, because there are 5 shapes. If we were drawing F, how many boxes? 7, because there are 7 shapes. Yay, my crowd's so good here, so good. We are going to draw half arrows to represent electrons, just to show it has a 1/2 spin. And remember that it's a positive 1/2 or a negative 1/2. And a Pauli exclusion principle says that I can only have 2 electrons with opposite spins in each orbital. And since it has a value of a 1/2, that's why we're just drawing the half arrow. So I can have 1 up, 1 down for 1s. And if we're thinking about lithium here, then I know that lithium would go through 1s2, 2s1. So when I'm in the 2s, I just draw the 1/2 arrow there to represent that I have that 1 electron. So direction of arrow represents just the spin of the electron. Okay, in terms of Hund's rule, so for Hund's rule, we want to make sure that we have 1 electron in each orbital before we start pairing them. So we said that this was the same thing as like the empty bus seat rule. So I couldn't, if I'm looking at carbon here, let's look at this one. I can't just place this electron in that orbital and pair them, because that would be very unstable compared to this configuration here, because stability is exactly what we want. So Hund's rule, I want to make sure that we have 1 in each first before I start pairing, okay? Or empty bus seat rule. Our last principle is off-bow principle, and that means that we are filling orbitals in increasing order of energy. So if we had our F orbital here, our periodic table would actually look like this. So we have our S block, the rare earth metals would be our F block, the transition metals are the D block, and then the P block would just be what's left over there on the other side. But remember that helium acts like an S orbital, so helium's actually not part of that P group. And one more thing, in terms of energy level, so we may be in that 6th energy level, but remember F goes down by 2 and D goes down by 1. Okay, in terms of electron configurations, we could do the longhand electron configuration by saying the 1s2, 2s2, 2p6, 3s2, 3p6, so on and so forth. But we also have that shorthand version, the noble gas configuration. Remember that consists of 2 parts, core electrons and valence electrons. So when we did the noble gas, the core electrons was represented by the noble gas. And then the valence electrons are those outermost electrons that I show after that noble gas configuration. We'll do some examples with this tomorrow in class. And we are going to stop right here, my children. Yay! Okay, so I will see you tomorrow. You have a wonderful night. Bye!